Love that intro. Welcome back to the second talk of Shiny Block. On deck, we have Noah Kantrowitz with What Python Can Learn from Other Languages. Please welcome Noah.
Excellent. I am indeed Noah Kantrowitz. I'm an SRE at Geomagical Labs. We do computer vision and augmented reality stuff for IKEA, but I'm not here to talk about that today. And I'm also not really here to talk about Python. Python is great. It's my primary tool for solving most technical challenges, but there's a lot of other programming languages out there, and some of them have features or workflows that Python lacks. The goal of this talk is not to immediately advocate that we turn each of these features into a PEP. We want to broaden our exposure to programming concepts and talk about the trade-offs being made. If any of these ideas really grab you, try messing around with them in a library or make a patch for CPython, but really, we're just here to learn. I'm going to begin with PHP, and I don't mean this ironically or to be some kind of language hipster. PHP is pretty cool. I spent the last few years on a side project almost entirely in PHP, and it's given me a refreshed appreciation. The biggest thing I've grown to like about it, the simplicity. Each file maps unambiguously to a single URL, and deployment is as simple as updating that file in any way you prefer. Most editors these days support remote editing via SFTP, so you just click on new file, you start coding, and that's it. This puts even low boilerplate web frameworks in Python to absolute shame. And once you get going, changes in the code, they just show up. You don't need to restart a server or configure automatic reloads or whatever. You just write code and it runs. Simple as that. In Python, we like to say that explicit is better than implicit, and overall I agree, but man, are juggling imports annoying sometimes. Even with editor help, you've got a dance of you write a new line of code, you realize you don't have the import in place, you scroll to the top of the file, you add the import, you scroll back down to where you were, but you've lost your train of thought. It's really jarring. Autoloaders bridge this gap while keeping things mostly explicit. If you enforce a one-to-one mapping between code symbols and file system paths, you know exactly where a symbol load is going to end up. This is also deeply integrated into the PHP package manager called Composer to pre-bake the mapping between those code symbols and the underlying file system paths, so the import doesn't even have to traverse a package directory. I don't actually know if I would honestly prefer this in Python, but it's at least something to think about. The standard library for PHP is a little bit different from Python. It's evolved towards a single niche, web application development. So it biases towards things needed in that space. So for example, MySQL and Postgres clients come by default. There's also a high-performance HTTP client. And then beyond that, there's this thing called the PHP Extension Community Library, or PECL. An extension PHP is very similar to an extension library in Python, but the big difference between PECL and PyPI is that for a lot of the big core supported extensions, the documentation for them is right alongside the main PHP docs. You don't have to do search for a library and then find its README or read the docs or whatever. It's all just there. PECL effectively bridges into a broader secondary standard library. And alongside the standard library being adapted for its major use case, PHP as a language is itself too. It's web first, so there's a simple templating framework baked directly into the language. In Python, we have f-strings now, and they've matured over time. We've definitely started moving in this direction, but relatively complex PHP code is, again, going to run circles around Python's explicitly simplest web frameworks. Ruby is probably the second most language used over my career, and while the days of Python and Ruby being thought of as relatively neck and neck have waned as Python's taken over more and more niches, it's still a vibrant language and community. Symbols are a thing in a lot of languages, but I'm going to highlight them here. At their simplest, symbols are just fancy strings, but internally they're deduplicated, so checking equality between two symbols is a constant time operation. We do have this in Python, sys.intern and intern strings, but they're very rarely used. But there's this deeper level to symbols. Having a dedicated syntax for this makes it easier to differentiate between text strings and, for lack of a better term, symbolic strings. These often serve very different functions in code, and even if they're the same underlying data type, they really shouldn't be mixed. We do already kind of have this a little bit in Python with the keyword argument syntax. Those are still strings under the hood, but they're clearly intended to be used for a different purpose, and you create a boundary between what kinds of use cases you want those strings to be used. Blocks are something much more specific to Ruby. Deep down, we do have this in Python. You can write a lambda expression as an anonymous function value, but blocks do a lot more than that. First off, they're not limited to a single expression. That's handy for anything complicated. But more importantly, that calling syntax with do, you can hang a block off any function in Ruby. Now, you can pass around lambda literals in Python. It's technically possible. We all sometimes do it when we're writing sort keys, but the utility falls off really quickly after that. And so community practice is that you'll write a named inline function and then you'll pass it around as a value. Totally works, but it does have this problem that the read order is now inverted from the execution order. And this gets even worse when we start talking about method chaining, something Ruby really excels at. I'm not even really going to touch the Python built-in functions, which are completely backwards from this, and I hate it. But you can write a method chaining API in Python, for instance, the Django ORM. But blocks allow it to go a lot further without additional effort. And another language that has a different take on this is Dart and its double dot cascading operator. This allows interrupting a method chain to go one level up, so to speak, like in a file system path, performing a sequence of operations on the same object rather than having to propagate the chain through every link in it. This allows method chaining in Dart with zero extra work by API authors. Another place Ruby makes excellent use of blocks is its version of the builder pattern. Many complex object constructors take a block which exposes a little configuration API, almost a DSL. This can allow for very complex initialization while still being compact and without sacrificing flexibility for unusual conditions, and it's very nice for things like static analysis, type checking. Going a bit broader than Ruby as a language, one big thing that Ruby has as a community that I wish Python was better at is the Ruby for Good organization. It's a dedicated support structure for Ruby projects which work with specific nonprofit organizations. We have a lot of paths for advancing Python itself and some of the bigger languages like Django, but sometimes it's nice to do real tangible good in the world. After Ruby, the next logical place to look for ideas are the JavaScript and TypeScript worlds. I'm not going to repeat every feature shared by all these languages, like how JavaScript also has a great anonymous function syntax. We'd be here all day. I'm just going to focus on some of the interesting bits. This one has been discussed at great length in the Python community, but I personally think they should be added, and it's my talk, so one more time. Null coalescing operators are very similar to an OR, but they're checking explicitly for nulls rather than any kind of falsy value. Safe navigation operators build on top of that. You can access a deeply nested chain of fields, but if anywhere in the chain there's a null, the whole thing stops and just returns a null right there. As you can see in this very small example, safe navigation operators dramatically streamline code. This is something I deeply miss when I'm working in Python. TypeScript has always had a fine line to walk. It applies type semantics to JavaScript, but it can't fundamentally reshape the language or be too alienating. So they knew the majority of object passed around within a code base were going to be the JavaScript equivalent of just a plain dict, no matter what. They also wanted to allow typing information to be gradually added to a code base. Out of this comes the synthesized requirement to support type declarations against arbitrary inline dicts. In Python terms, this is kind of similar to a data class, but it's completely ad hoc and without requiring either the upstream or downstream code to change. This certainly isn't as nice as a fully typed code base, but it gives a smoother on-ramp to doing one bit of code at a time. I'm kind of cheating here. We do have promises in Python as part of the concurrent features library, and perhaps their moment is over anyway, with the continued uptake in explicit async await, as Chris so rightfully pointed out. Most of those APIs are now what you'd use in Python, and even in other languages too. But they're still worth studying, even as only part of our collective history. Promise chaining is a compact way to handle multiple interacting concurrent operations without dedicated syntax. I'm pulling my punches with this a little bit. This is a really simplistic example, and in practice, many promise chains were a lot harder to read, but perhaps the technique will find another application someday. On the topic of concurrency, Go. It's no secret that Go's structured concurrency has made it a frequent choice in complex systems code. And honestly, I think Python's already heading in a lot of the same directions. If you've seen anything about Go, it's probably this. Go routines are a concurrency mechanism, more or less the same as we have with async functions, except they're truly concurrent. And channels are queues to move small bits of data between them. I think this model is about to get very interesting in Python, as we've seen the addition of both GIL-isolated subinterpreters and the new no-GIL mode. There's a future where we get something very similar to the code on screen, but with full multi-core concurrency. Runtime type checks are something Python has always kept at arm's length. We do technically have it. There's that runtime checkable decorator that comes from the typing module. But as the docs warn you very emphatically, all this does is check that the right method names exist, not their type signatures. Compare this to Go's runtime casts, which do a more complete check, and they can either fail with an error message or just straight up crash your program, whichever you prefer. This would require that there would be something in CPython itself that understands how to compare type signatures, but perhaps we've come far enough in our type hinting journey to be ready for that. In a totally different direction, Go is among the best in class alongside Rust with preparing easy standalone executables as well as cross-platform compilation. In the server world, this makes deployment really easy inside minimalist containers. All you need from the OS is some TLS certificates, maybe a time zone definition file or two. And for command line tools, you can distribute a single binary without concern for the system library versions or anything else. Briefcase has relatively recently added some simple CLI packaging support, and I'm hopeful that it will improve things here. Make Rust make this better. Unikernels build on static compilation and take it a level deeper. Rather than linking in the language runtime and maybe libc and some other files, what if we statically link an entire operating system? Unikernel frameworks take your app code and they turn it into a bootable OS image designed to run in a hypervisor instead of Linux. While containers kind of took the sails out of this technique, it can still matter when you want to get every last bit of performance out of your hardware while also ensuring absolute maximum security isolation. There are tools out there like Unicraft that can do this today, but they're all general purpose tools. They lack the deep integration into Python to really make them shine. If you're only here for things that have even a tiny chance of happening in Python, I wish you well, but now I want to look at a little bit of the long tail. Weirder features that you maybe have heard about, but it's really unlikely that Python will actually probably discuss adding these at any point. Even against those long odds, I still think there are things here to learn. On the complete opposite end from packaging is easy one-liners. Perl has a lot of interesting design elements, but by far the most useful for me day to day is PerlPy. It's a sequence of command line arguments that says, take this list of input files, run this expression against every line of every file, and then write the results back to those files. Taken together, this allows for a superset of things like sed and awk and bash, but in an incredibly compact package and without the myriad of provider differences between all those tools that have occurred over time. Now, making a Python version of this in a library would be easy, and they are out there. You can use them. But one of the real values of PerlPy, you can drop me onto pretty much any server made from 1995 onwards, and there's probably going to be a Perl binary on there somewhere. Maybe if we added this to Python in the standard library now, it could be similarly omnipresent in 10 years. LINQ is short for Language Integrated Query, and it's basically, what if SQL was our API? This is most direct when it's used as a type of ORM, and that is definitely the most common use case for it. But C# took this even further, and you can build arbitrary providers on top of LINQ to make it do anything you want. Python has taken some baby steps down this path. We have cross-library standards for data frames, and you can put DuckDB on top of those to get SQL-like exploration. But what if that was a language syntax that anything could plug into? Call with current continuations will take some explaining, so just bear with me. At a basic level, it's a kind of non-local return, like an exception. And indeed, we can do a very basic implementation on this in Python using exceptions. So we take a function, we want to run that function. The function will receive one argument, which is itself a callable. When the function wishes to return, it should call that callable with the parameter being the value that it wants to return. This alone would be pretty boring, though. The real power of continuations is that in some languages they can be moved around, stored as variables, or even serialized to disk, all allowing you to jump right back to the point of the code where the continuation was generated. This makes it something like a structured goto. Imagine being able to save and restore the state of a generator function as if it were any other object. I wrote that line, but you don't really have to imagine because Chris showed us how to do that. But what if it wasn't like that? While continuations are mostly associated with Scheme, they are very effectively used in the Smalltalk web framework Seaside. In Seaside, the whole state of the application is managed via pickable continuations. So in that Smalltalk code up there, that invocation of color picker, this is inside a web app, so that invocation of color picker is going to return an HTTP response to the client telling some JavaScript to please open a modal showing a color picker, wait for the user to do a thing, get a response, then send that back as another request up to the server where the server will unpickle the continuation and pick up right where it left off in the code. So this is all the benefits of the cleanliness of a single-page client-side app, but in server-side code. And because I really love how Smalltalk does flow control, here's a really rough port of some of it to Python. The short and important version of this, Smalltalk doesn't have special syntax for flow control. So, for example, if is a method of the bool object, and so is while. There's an example of each of those up there if you can read them. In practical implementations, these don't actually happen. They get compiled into special constructs because we want code to run quickly. But it's a great example of doing more with less in language design. And if you want to go even more minimal, you can look at tiny fourths. You can bootstrap a whole language interpreter with a few hundred bytes of assembly, 20 to 30 keywords. From those, you build a basic parser and then an interpreter loop, and then some more control flow, and then an entire program. Fourth kernels have been written as small as 400 bytes of machine code. Minimalism isn't really a specific goal of Python, but it's a good reminder of how little is needed for a productive system. What would a minimal Python look like? What's something that would be just powerful enough to write all of the rest of Python? Another interesting blend of language features and frameworks is Erlang's Open Telephony Platform, or OTP. Specifically, the supervisor system. Erlang programs are, to use Python terms, a series of interacting async tasks all running in parallel. We can do that in Python today, but what happens when one of those tasks crashes? It's often difficult to sort out how to respond exactly. OTP applies similar concepts from the server and container management world, but to individual tasks within a complex application. We can set the supervisor to restart a failed task automatically, or have a custom restart behavior, like waiting a certain amount of time, or we can set up a dependency tree so that if any in the tree crashes, it restarts the entire set to ensure consistency. This is how Erlang builds incredibly high uptime systems like phone switches without magical programmers who don't write bugs. This could mesh well with the sub-interpreter work we looked at before, and in fact, Go's coroutines and channels were heavily influenced by OTP's server and mailbox model. There could be a future where we have something like task groups, not just as a synchronization mechanism, but also for runtime supervision. Python has made incredible inroads as being the language of choice for scientific computing and data science, but in almost every one of those applications, you'll find Fortran under the hood. Most people think of Fortran as part of our technical past, but it's very much alive, and for good reason. Fortran is almost perfectly designed to be able to write complex mathematical algorithms, which can then be compiled to the fastest possible implementation on each platform. So rather than maintaining a separate linear algebra implementation in assembly on every OS, we have a single one in Fortran, and we trust in the toolchain. Even C can't compile things as effectively as Fortran in a lot of cases, despite most of us thinking of C as the lowest level thing out there. Specialized use cases need specialized tools. And while Fortran is still alive and well, COBOL is mostly, though not entirely, in the rearview mirror at this point. But like we talked about with PHP, it's fun to look at language features that grow from a tool with a single primary purpose. In COBOL, I think the most interesting part is the data division. In modern terms, every COBOL program carries around the schemas of the databases it expects to read from and write to. While these days it would more often be a network API rather than a structured file on disk, we have basically the same problems to solve, with producers and consumers of data agreeing on schemas while still allowing that schema to evolve over time. COBOL's implementation isn't perfect. It comes from a time where those schema changes were expected to take months instead of hours, but I've worked on a lot of projects that are decades newer and have substantially worse schema management. Homomorphic encryption is probably the most out there of all these. It's barely even a programming feature and more of a cool math trick. The idea is doing computation on encrypted values without decrypting them. So this means that you have data processing code that takes encrypted data that it does not have the decryption keys for. The core way that this works is, instead of thinking of your code as lines of code compiling to machine instructions that are evaluated on some kind of virtual machine, we're instead going to compile your code into effectively a virtual ASIC, digital circuit gates that'll implement a homomorphic encryption flow. Given those constraints, there are, of course, very hard limitations in the kind of computation that you can do, and also it's still pretty slow. But in an increasingly privacy-conscious world, maybe this is worth more of a look from all of us. I started off by saying I wasn't aiming for you to go off and turn these ideas into PEPs, and while that is true, I wish it wasn't. A few of these ideas could probably be prototyped in libraries and gain some traction there, but most of these, to really succeed, they would need a core language change. The process for that has improved over the years, but the steering council has to walk a really fine line. Adding anything into CPython is a big commitment. It can't just be experimental and it'll go away in a little bit. So this leaves us in kind of a bind. To get peer support for a change, we need to prove that it's a good idea, and for that, we need people to be able to play with it. But for people to be able to play with it, we need to get a core change in, and we can't do that until we have peer support, and now we're stuck. Macros are a language construct to allow metaprogramming inside the language itself, adding a new experimental syntax, or changing some syntax that's already there, or writing your code in Route 13. The sky's the limit. The two best places to look for ideas about macros are Rust and Lisp. C does heavily feature macros, but it takes a much less structured approach, treating source code more as just text to be templated. And that does technically work, but Lisp and Rust show us a deeper power, defining macros in terms of the symbols of a language, but not its syntax, so that we can create our own. Python does have a proposed macro system, heavily influenced by Rust's, but it has fallen into the same trap as we were trying to escape by having a macro system in the first place and has received little discussion over the years. I want to talk about how Lisp does macros. Before we can do that, we need to talk about how Lisp code is structured. And before that, we need to talk about how Python code is structured. So like most other languages, Python's parser produces an abstract syntax tree. This isn't bytecode. This is a highly structured representation of your code text. And it's ready to be handed off to the compiler and other layers for further execution or optimization. Lisp does have something like that, but it's way simpler. Lisp has almost no actual syntax. Everything in Lisp is one of two things: an atom, which is their word for a symbol, which we talked about before, or a pair of two things, each of which can again be either an atom or a pair of two things. This is just the barest bit of structure, but it also means that macros in Lisp can do almost anything as long as the input and output are both S expressions, and basically everything can be an S expression. The way def macro works in Lisp, so we've parsed the code into an S expression, and something is going to start spidering out over that code looking for special atoms. Def macro itself is a special atom, and it takes the name, the parameters, and the body of the macro, and it registers that name as a special atom. And it's going to continue spidering out of the code. If it sees that name, it'll say, it's a special atom. I know what to do. I will go find the body of that macro. I will take the arguments, which remember are still symbolic. The code isn't running. It's just been parsed. So we have the symbolic arguments. We'll slam them into something. We'll evaluate the body of the macro. We'll get back another expression, and we'll just plug it right in where the macro's special atom was. The important takeaway here is that macros break the usual flow of things. Usually our code is going to move linearly from tokenizing to parsing to compiling to executing. There's a couple of newer steps in there. You'll see JIT compilers and stuff. But the key with macros is they put a little subloop inside the parser step, compiling and executing the body of the macro and returning the output to the parser. This may seem like a minor thing, but it's the pressure relief valve that lets us extend the parser without explicit support from the language. Rust has two main types of macros. Procedural macros are the equivalent of what we saw in Lisp. There's a couple flavors depending on exactly what kind of parsing you want to hook into, but they all take a stream of tokens and they return a stream of tokens, which means they can do basically anything. They can even operate on things that aren't valid Rust syntax in the first place. And that's cool sometimes, but most of the time when we're writing a Rust macro, we just want to slightly tweak the syntax that's already there, and we use declarative macros with this thing called macro rules. Declarative macros are very similar to Python's match case statements, but again, the code isn't running, it's just been parsed. So the parameters are symbolic expressions or types, and the code block is returned rather than being executed. It does support a little bit of like templating expansion basically, although I can't really go into the full power of this in 30 seconds, so hopefully this gives you just the barest idea. The core idea is that basically anything can be prototyped inside a macro without explicit support from the Rust team. So why look at all of this? Personally, I just think it's fun to see what else is out there, but if that's not enough, I certainly hope that learning about these patterns and systems can help you better organize your code and APIs in Python, or at least shows you what other tools are out there, and in the end, that makes us all better developers. Thank you very much. Any questions?
Thank you, Noah. We do have time for questions. Okay, we have a question.
Hello. Of those lists, you mentioned this is Python ideas, but not Python ideas. Which of those Python ideas do you think would be most likely to be implemented, or to actually land in core? And which one do you think would be the highest yield if it were, reflecting on Chris's comments about the fact that generators were implemented, which then made all these other things possible?
I think safe navigation, I mean, I wasn't kidding that I think they are. It is a mistake that we have not included them. I think that would probably be the highest value one. It makes it much more likely that people will write good error checking in exploring deeply nested objects, which is a thing that a lot of code these days does, especially as we're trying to push more people into using structured typing things like data classes or adders. We can't just call .get on there and assume that it'll figure itself out. So I think safe nav operators for the second one. The one that is most likely, I don't even know anymore. The core team is an inscrutable box to a lot of us. Somebody is pointing that way.
Pointing. Oh, yep.
Yeah, hi. So you talked about what you'd like to see added to the language. I'm interested if you've got any ideas of things you'd like to see removed, maybe something that's non-standard compared to other languages that you'd like to see standardized across the board.
In practical terms, I would like nothing removed because I remember the Python 3 migration period, and breaking compat like that should never happen again. And I'm pretty sure that we have all convinced ourselves that it never will again. So in practical terms, I think anything that has been out there, that ship has sailed. If I could wave a magic wand, though, the one I actually ask that question when I'm doing interviews, the big one would be packaging. I think no one is under any impression that Python packaging is in an amazing state. I would make that I would make Python push all of that into a better direction. If I could remove one thing, it would probably be multiple inheritance. I think it does more harm than good and always has. Class decorators should have been the correct solution there, and I think most of the people these days, they use that instead, but multiple inheritance just breaks a lot of stuff in mysterious ways. My understanding of that is that Guido read a paper, thought it was really cool, and implemented it that night, and it was early on enough in the Python ecosystem that no one could tell him no, so he just merged it, basically because he thought it was shiny, which not really how we do language design anymore.
Hi, I'm one of the DuckDB devs. I'm curious to see what you would, or what you think that would look like integrating DuckDB or another SQL engine into Python itself.
Probably a lot like it does in C#. Link, there is a special keyword. I think it is literally just select because they wanted to model it off SQL because that's what most people know. And once it sees that keyword, it moves into an alternate parsing mode that, again, very closely resembles SQL. And it would just, probably the simplest version is just, that would be a very fancy quoting syntax that would just hand that off to something else. There would be a provider registered. We've talked about this, I think, a bit with tagged strings of various types, being able to register, like we have F strings and R strings. You could have a duck string. And that would certainly be a lot closer, but I like things like type checking, and it would be a lot closer to being a core language feature if it was more deeply exposed as part of the language.
No other
Thank you very much.
questions? I think that's it. Give it up for Noah.